Hello again. This is Math 1120 coming to you from the College of DuPage, and this is the conclusion of the lecture entitled Applications of Newton's Laws. Please be an active learner as you watch these videos. Let's do an example of a car on a ramp. So you see this car is on a ramp. Oh, I guess I will read it. An object resting on an inclined plane. A car with weight of 1.76 times 10 to the 4th newtons rests on the ramp of a trailer. So here's the trailer. That's making an angle there of alpha with a horizontal. The car's brakes and transmission locks are released, and only the cable prevents the car from rolling backwards off the trailer. And the angle is 26 degrees with the horizontal. Find the tension in the cable and the force with which the ramp pushes on the tires. So here is our diagram. And you see what happens is that the force that the ramp exerts on the tires is going to be the normal force. And we have the weight of the car is pressing downward, and that can be resolved into vertical and horizontal components. And so we replace the weight with those components, and then we have this in equilibrium. So we first find the components of each force and then apply Newton's first law. So to find those, then what we're going to do is we can look at this and see that T has to be the negative of W sine theta. So that means that if you add the two together, you get 0. And similarly, the normal force has to be the negative of this force that is perpendicular to that. And so we have these two equations, and these are easily solved. You just move the W sine theta and the W cosine, W sine alpha and W cosine alpha to the other sides, and you get this is the solution. And now we know what W is. W is 1.76 times 10 to the 4th newtons. We can find the sines and cosines, and we find out that this is T and this is N. Here's another example, lifting granite and dumping dirt. So the idea is it's another inclined plane problem, but this time we involve two objects that are tied together by a cable. So you see this cart and this bucket are tied together with a cable. So blocks of granite, each with weight W1, are being hauled out of a 15-degree slope from a quarry. And for environmental reasons, dirt is also being dumped in the hole to fill up the old holes. So you've been asked to find a way to use the dirt to move the granite more easily. So you design a system that lets the dirt weight, and this is weight W2, and that includes the weight of the bucket, that drops vertically into the quarry, and that pulls out the granite block on the cart. And the total weight of this, including the cart, is W1, rolling on steel rails. Ignoring the weight of the cable and friction in the pulling wheels, determine how the weights W1 and W2 must be related to move at constant speed. Now, constant speed means we're in equilibrium. What happens is that we find, here's the diagram that we have, and so what we find is that the looking at the up and down, the Y kind of things, that the tension in the cable plus the weight is equal to 0. So that means the tension is equal to the weight. This is the negative of the weight. The tension is the negative of the weight. And so then we will also look at the summation of the forces in the x direction. And so the x direction is going up and down the cable, or the inclined plane, excuse me. And so here we find that this one, which is W1, W1 sine of 15 degrees, has to be equal to the tension. And so we're going to be able to set this one, W2, equal to this one, W1 sine theta. And sine of theta, or alpha, I guess we called it here, is 15 degrees, so that is 15 degrees. So you see W2 has to be 0.26 W1. So we have solved for the relationship between the two. So in this example, we're going to use Newton's second law to calculate the acceleration of a key hanging in a car. You tape one end of a piece of the string to the ceiling light of your car and hang a key with mass m on the other end. A protractor is taped to the light, and this allows you to measure the angle the string makes with the vertical. Your friend drives the car with a constant acceleration, that is the one here, and with a magnitude to the right. The string hangs at rest relative to the car, but makes an angle beta with the vertical as the car is accelerating. So you want to know what's an expression for the acceleration in terms of the mass m and the measured angle beta, and in particular what happens when what is a when beta is equal to 45 degrees and when beta is equal to 0. So that's what we have, and this is the force diagram that we make. So we have a tension that is there, and the tension in this little rope is, which is a force, is resolved into this kind of a force, a horizontal force and a vertical force. And the force going down is m times the acceleration due to gravity. Okay, now this is not an equilibrium problem because you see it's not an equilibrium. We are accelerating. So this is going to be F net equals ma. So the string and the key are at rest with respect to the car, but the car, string, and all are accelerating in the positive x direction. Therefore, there must be a horizontal component acting on the key. So we'll use Newton's law in its component form. The sum of all the forces, the net forces in the x direction, is m times the acceleration in the x direction, and this one in the y direction is going to be m times the acceleration in the y direction. Well, we know what we have in the x direction, because you see that is going to be t sine beta. And in the y direction, it's going to be this one, t cosine beta minus mg. So that's what we have, and so we know that in the x direction that's going to be the acceleration in the x direction, and this is going to be equal to 0 because those balance. It only moves t alpha. The net acceleration is going to be 0. So if we rearrange the terms, then we get that t sine beta has to be equal to max, and t sine beta is equal to, and that really should say t cosine beta. I'm sorry, that's a typo. That should be cosine beta there. And what we're going to do is we're going to divide these two equations. So we're going to take this equations and divide it by this equation. Now the t's will cancel, and we'll have sine over, again, this was cosine. That makes it a tangent, and the masses will cancel out, and so we will get, and then when we solve for ax, we will know that ax equals g tangent of beta. You should check on this, and they already corrected their error, so this one is correct, even though that one right there should say cosine of beta. So the acceleration ax is proportional to the tangent of the angle. So the bigger the angle, the more the acceleration. Now when beta equals 0, the key hangs vertically, just straight down, and the acceleration is 0. When it's 45, it forms an isosceles triangle, so what's going down has to be the same as the horizontal, and that means that A is equal to G in magnitude. And here's a practice problem if you want to practice with some more numbers. We can also talk about an acceleration down a hill. So here you have some folks riding, you can think about that on a sled down a hill. So we're looking at the problem where an object is sliding down a frictionless, we're assuming there's no friction, inclined plane. And there's a toboggan loaded with some students. Their total weight is W, and it slides down a long snow-covered slope. It slopes at a constant angle, alpha, and it's so well waxed that there's virtually no friction. So find the acceleration and the magnitude in of the normal to the hill that exerts on the toboggan. Well, we draw our picture like this. Now this is the hill, and so the hill is here, and the weight of the toboggan, which was called W, is going straight down, but that can be resolved into these perpendicular components. One is going down the inclined plane, and the other is normal to the inclined plane. Okay, so now what we're going to do is, there's only one x component of the force. So what happens is that the net force is going to be W sine alpha. There is no friction. So that's the only thing that you have, is this force pushing you down. So that's what's happening there. But we also know that the summation of those in the x direction, where x is going down the inclined plane, is going to be mass times acceleration, because you are going to be accelerating. So we set these two things equal and solve for the acceleration ax. Now W is equal to m times g, so the m's will cancel out, and you can solve for ax is going to be g sine alpha. Now the y component really says that this normal plus minus mg cosine alpha is equal to 0, so the normal is equal to mg cosine alpha. So this is the normal, and this is the acceleration in a direction. Now, and if you wanted to do a problem that had final answers, suppose you knew that the acceleration was g over 2, what would the slope, what would be the slope, the angle here? And the answer is going to be 30 degrees. Now this is almost an exit problem here. We're talking about, gee, do you understand what's going on here? So the carts in this figure, so you have cart A, rope 1, cart B looks bigger, and rope 2 are speeding up as they are pulled to the right. Now speeding up means there is an acceleration to the right with increasing speed across, and it's a frictionless surface. Assume the ropes have negligible mass, so what can we conclude? A, the pull of rope 1 on cart A has greater magnitude than the pull of rope 1 on cart B. The pull of rope 2 on cart B has a greater magnitude than the pull of rope 1 on cart B. Or C, the pull of rope 1 on cart A has a greater magnitude than the pull of rope 2 on cart B. And here are your free body diagrams. And the correct answer that you should get is B. You see, for cart B to accelerate, there must be a net force to the right. So answer A cannot be correct. If the rope is massless, the forces acting on the two ends must add to 0. Nor can answer C be right. The two carts have the same acceleration. Therefore, the tension in rope 2 must be great enough to give the acceleration to both carts, while the tension in rope 1 is just great enough to give cart A the same acceleration as shown in the free body diagram. So that means the answer must be B. Now, we've talked a lot about frictionless things, and I'm going to talk very briefly about friction, because friction is a contact force between two objects, and it's always represented in terms of the normal component to the surface. You see, the harder that you're pressing down to the surface, between the surface and the body, the greater the friction. So it's going to be proportional to that. And the force is there's a constant of proportionality called mu k, and this is called the force of kinetic friction. Now that means if it's already moving, how much do you have to exert to overcome that friction? Now, if there's no relative motion, the maximum possible force of friction is proportional to the normal force, and a different constant, which is called the coefficient of static friction. Here you're just getting it started, and you see it takes more work, more force, to get something started than it does to keep it moving. And here's a picture showing you how these forces are. You see you're pulling here with the tension, but friction goes the other way. It retards your motion, and static friction is greater than kinetic friction. And this can be really quite complicated. But I did want to talk about it a little bit, and here's why. The coefficient of frictions are out of the scope of the 1120 course. I'm not going to be talking about this any more than this. But later on in ultrasound, we will talk about coefficients of attenuation at boundaries between different tissue types. And those are in scope. So having these coefficients makes sense for us to understand that as we go forward. Okay, last thing we're going to talk about in this section, actually almost the last thing, are elastic forces. Now, when forces act on an object, the object sometimes, in fact usually, deforms. In some cases, such as a stretched or compressed spring, the amount that the object is deformed, delta L, the change in the length of the object, is approximately proportional to the magnitude of the applied force. And this is called Hooke's law. And Hooke's law says that the force required to deform the spring, delta L, a change in length of L, is proportional to, and the force is proportional to the distance it deforms. And there's a thing here called the spring constant. So if you have a big spring, there'll be a large spring constant. If you have a small spring, you will have a small spring constant. So what happens is, if you're in the equilibrium position, nothing is happening. But if you push this in delta x this way or x this way, it's going to be kx is the force. And if you pull it out this way, it is going to be k also. But notice that this force and this force are the same magnitude, but they're in opposite directions. So when stretched or compressed from equilibrium, the spring exerts a force, F spring, whose magnitude is approximately proportional to the displacement. That's the theory. So here we're going to talk about an example called fishy business. Now here what happens is you have a spring that you're going to use to weigh something, but then you're going to put some fish in this, okay? And the delta L, the length of the spring that changes when you put the fish in there, is going to be 1 centimeter. Now you do want to think about that being 1 centimeter. So here's what we got. Suppose that a spring balance used to weigh fish is built with a spring that stretches 1 centimeter when a 12.0 Newton weight is placed in the pan. When the 12 Newton weight is replaced with a 1.5 kilogram fish, what distance does it stretch? Okay, well, what you're going to have to do is you're going to have to say, oh, up here I know that the force is 12 newtons, and that makes 1 centimeter. So you see what you can do is you're going to say 12 newtons here is equal to K, and that is 1 centimeter. Now you want to be careful because these units are centimeters, which is times 10 to the minus 2, and this is going to be meters. But we can look at this equation and we can say, all right, this data point tells us that K has to be, and it's always the same spring, it's going to be 12 newtons divided by the length, and so the spring constant is 1200 newtons per meter. So then we know the weight of the fish is going to be the mass of the fish times 9.8 is 14.7 newtons. So now what we're going to be able to do is say, for this to be an equilibrium, when you put the fish in there, the summation of the change of forces in the y direction have to be 0. That's mg is equal to the force of the spring. And so what you do is this is going to be minus 14.7 newtons. That's the weight of the fish. And this is the force of the spring. And so we can solve for delta L. and you see delta L will tell us how long it stretches. So we're going to use our this equation, and we're going to solve this for delta L. So delta L is equal to, and here we can get it in meters, or here we can get it in centimeters. It's 1.23 centimeters. And here's another practice problem you can do if you want to about this kind of problem. Also, many mattresses have inner springs. So if you just bought an interspring mattress that contains coil springs in a rectangular array, 20 coils wide and 40 coils long, you estimate that when you lay on the mattress, your weight is supported by about 200 springs, about 1/4 of the total number of springs. You observe that the springs compress about 2.6 centimeters when you lay down, and assume that your weight is 800 newtons, is supported equally by 200 springs. What's the force constant? Well, so you see what you got is the force of the spring is pushing up, your weight is pushing down. So to be in equilibrium, the total upward force must be 800 newtons to manage the weight. So the mass, which is, not mass, excuse me, the 200 springs times the force of the spring constant, and this is how much they're being compressed, has to be 800. You can solve for K. So K is equal to 1.54 newtons per centimeter. And again, here's another problem if you want to test to see how you do on that. And here you have numerical answers. Okay, this is to test our understanding of section 5.4, and this is a spring on the moon. An astronaut standing on the moon hangs a 5-kilogram mass from a spring. If the spring constant is 320 newtons per meter, by how much does the, that should say spring, not string, spring stretch? And the acceleration of gravity on the moon is less. It's not 9.8 meters per second squared, it's 1.6. So what you're going to be doing here is you're going to say the downward force is simply its weight, that is mg, but that's going to be this number. So what you're going to do is you're going to say KL is equal to mg, so delta L, how much the spring stretches is, and you do mg over K, and you get 2.5 centimeters. Now, 5.5 really is a concept chapter, no real problems, but does say there are gravitational forces, like the moon and the earth. There are electromagnetic forces that connect the strands of DNA. There are nuclear forces, and there are also weak forces at big distances. Now, the point is, forces are big in all of this study, and even in ultrasound, forces really matter, and we will talk some about that when we get to talking specifically about ultrasound. And ultrasound also occurs in nature. We talked about the bats. That's all I really want to say about section 5.5. And here is low stakes assessment 12. A 2-kilogram block is launched up a frictionless inclined plane. You're launching it up with a spring, so you squish it down and do that. So the plane is inclined at 30 degrees and the spring constant is 1,000 newtons per meter. The block is initially pushed against the spring in order to compress the spring by 0.1 meter, and then it's released. So you're to calculate the magnitude and direction of the acceleration of the block the moment after it's released. Calculate the acceleration when the spring reaches the point where its compression is 0.5 meters. And what are the magnitude and direction of the acceleration when the spring reaches the point where the compression is 0? It's a good problem, and this will be due in about a week or so. Now, that's really finishing Chapter 5 for us. Chapter 6 is out of 1120 scope. It's not saying it's not important, it's just people are going in circular motion here, and we will not need to study circular motion to talk about the ultrasound stuff that we're talking about. So this is out of 1120 scope. Doesn't mean it's bad stuff. It's just that's something we're skipping. And we're going to be talking about kinetic energy and potential energy next. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. God bless you all.